Welcome back. In this video, we're going to look at example problems involving plane curves and parametric equations. Let's get to it. Alright, so here's our first example. We want to sketch the curve represented by the parametric equations and find the corresponding rectangular equation by eliminating the parameter. Alright, so we have a set of parametric equations here. We have x is equal to t divided by 3 plus 3, and y is equal to 2 times t minus 4. And t is our parameter in this case, and t is defined for values from 0 to 3, including each of those values, since we have less than or equal to signs. Okay, and so the first thing that we want to do here is eliminate the parameter in our parametric equations, and that is going to help us sketch the plane curve that these parametric equations represent. And what I mean by eliminating the parameter is we're going to create an equation of just x and y that doesn't involve t. And that's what we call a rectangular equation. Equations that you were used to using up until this point. All right, and the easiest way to do that is just to solve for t in one of your two parametric equations and then substitute what t is equal to into the other equation. All right, so I'm going to choose to solve for t in this equation for x. And so if we subtract 3 from both sides of the equation, we will have x minus 3 is equal to t divided by 3. And then if we multiply both sides by 3, we will find that 3 times x minus 3 is equal to t. Now if we distribute 3 through this quantity, 3 times x is 3x, and 3 times negative 3 is negative 9. So t is equal to 3x minus 9. All right, and now what we want to do, now that we have solved for t in terms of x, is replace t in our equation for y with 3x minus 9, and then simplify, and then we will have a rectangular equation in terms of x and y that we can use to help us sketch the plane curve represented by these parametric equations. So what we're going to have is that y is equal to 2 times 3x minus 9 minus 4, right? We just replaced this t with 3x minus 9. And remember to put parentheses around both of those terms because this 2 needs to be multiplied by both of them, not just 3x, okay? So if we simplify and distribute 2 through this quantity, 2 times 3x will be 6x, and 2 times negative 9 is negative 18. All right, so we will have y is equal to 6x minus 18 minus 4, but negative 18 and negative 4 will combine to be negative 22, so y is equal to 6x minus 22. All right, and so our rectangular equation here hopefully looks pretty familiar. We have y equals 6 times x to the first power minus 22. This is just a basic linear equation. This just represents a line. So in this case, our plane curve is not even really a curve, it's a straight line. However, we do need to figure out where that line begins and ends based on our values of t. We know that t is defined from 0 to 3. So this line that's represented by this equation is not going to continue on forever in the positive and negative direction. It only exists for the coordinate points of x and y that result from plugging in values of t from 0 to 3. So the way we can figure out what our two endpoints are, meaning the initial point of our plane curve and the terminal point of our plane curve, is by plugging in these values of t that are the endpoints of this interval into each of these parametric equations. All right, and once we have the initial point and the terminal point, then we will sketch our curve, or in this case, our line. So let's start by finding our initial point when t equals 0, right? That is our lower bound. That is the lowest value of t, and so that's going to give us our initial point when we plug in 0 into these parametric equations. So when t equals 0, x is going to be equal to 0 divided by 3 plus 3, but 0 divided by 3 is just 0, so x will be equal to 3. All right, so x is equal to 3, but then what about y? Y is going to be equal to 2 times 0 minus 4, and 2 times 0 is 0, minus 4 will be negative 4. So y is equal to negative 4. So our initial point, which I abbreviate with IP, is at the coordinate 3, negative 4. Okay, so if I clean up my work, now let's find our terminal point when t equals 3. And so when t equals 3, we will plug 3 into each of these equations. So x is going to be equal to 3 divided by 3 plus 3. That's a lot of 3's, but 3 divided by 3 is 1, then 1 plus 3 is 4, so x is equal to 4. And then for y will be equal to 2 times 3 minus 4. And 2 times 3 is 6, minus 4 is 2, so we know that y is equal to 2. And so our terminal point, or the point where our curve will end, will be at 4, 2. All right, so let me clean up my work again. We now have our rectangular equation that we can use to sketch our curve, and we have the initial point and the terminal point for that curve. So let's finally sketch it. Let's draw out our coordinate system. First, I'll draw the y-axis, and then I'll draw the x-axis. So this is the x, and this is the y. All right, and now let's start by plotting our initial point and our terminal point. Our initial point is at 3, negative 4. So I'm going to say that this is positive 3, and this down here will be negative 4. I didn't give myself a whole lot of room there, but counting down 1, 2, 3, 4, this is where negative 4 would be. And so that point will be right here. That's our initial point. And so I'll label that with IP. And then our terminal point is at 4, 2. So this will be x equals 4, and this right here will be y equals positive 2. And so our terminal point will be right here. And then I'll label that as well. So this is the terminal point. Okay? And so now these 2 points represent the beginning and the end of our plane curve. But our plane curve in this case is just a linear function. So we know it's going to be a straight line. There's really no curves for this plane curve, and so there's no need to really graph this entire line. We don't need to extend this graph and make sure that this linear function crosses the y-axis at negative 22. We don't need to worry about our slope of 6. All we have to do is just connect these 2 points, and we will have that line. All right, so let's do that. If we connect these points, this right here represents our plane curve. The only thing that we have to label yet is the direction of the curve. Which way is it going? Is it starting at this point and ending here, or is it starting at this point and ending here? Well, we already have it labeled that this is the initial point and this is the terminal point, but what that means is that this plane curve starts here and moves towards this terminal point. All right, so we want to put in some arrows that show the direction of that plane curve. Because really what a plane curve represents is the resulting path of the motion of an object in a plane, right? So this straight line is representing the path of motion for some object that is moving in 2 dimensions. So it's important for us to know where that starts and where it ends and the direction that it's heading. Okay, and so with that, we have now officially sketched the curve represented by these parametric equations. And then of course the other part of our problem was to find the corresponding rectangular equation by eliminating the parameter. That is this equation right here that we found at the very beginning. Okay, and so with that, let's take a look at another example. All right, so here's our next example. Once again, we want to sketch the curve represented by the parametric equations and find the corresponding rectangular equation by eliminating the parameter. All right, and so in this case, our 2 parametric equations are x equals t minus 5 and y equals the square root of t. Now in this case, we aren't given an interval for our parameter, and so what we have to do instead is determine the natural domain for the values of t. In other words, we just need to find the values of t that would make sense for our 2 parametric equations, which means that we need to determine what values of t our equations are defined for. Well, for our first equation, we have x equals t minus 5. That's going to be defined for all values of t. We can plug in whatever real number we want for t, we're going to get a defined value. But for y equals the square root of t, we cannot plug in any negative numbers, right? We can't take the square root of a negative number and get a real result. So we will say in this case that t is defined for all positive values greater than or equal to 0. Okay, so t can be any value greater than 0 as well as 0 itself. And what that means for our curve that we're going to sketch is that it's only going to have an initial point, not a terminal point, right? Our values of t are going to start at 0, but there's never an end point. T is going to go on for infinity. So another way that we could write the interval here, we represent that with capital I. The interval for our parameter is equal to the interval from 0, including 0, to positive infinity, not including infinity because infinity is not a specific number. All right, it just represents values getting larger. And so now let's work on eliminating the parameter. Let's find a rectangular equation from these parametric equations that we can use to help us sketch our plane curve. What we want to do is solve for t in one of these two equations. I'm going to choose to use this one right here. I see that we already have t by itself, so if we add 5 to both sides of the equation, we will have that t is equal to x plus 5. Now we can plug what t is equal to into our other equation, y is equal to the square root of t. So what we'll have is that y is equal to the square root of x plus 5, right? T is equal to x plus 5, so y will be equal to the square root of x plus 5. Now this is an equation that we are pretty familiar with, right? We know how to graph a square root function, and so we'll do that in just a second, but first, let's find our initial point for when t equals 0. And then we'll use that initial point as well as our rectangular equation to help us sketch our plane curve. All right, and I'm just going to box this in because this does answer part of our question. We did want to find the corresponding rectangular equation. That is this right here. But now let's find that initial point. When t equals 0, we're going to plug 0 in for t in both of these parametric equations. X will be equal to 0 minus 5, and so x is equal to negative 5, and y will be equal to the square root of 0, which is just equal to 0. So our initial point is just going to be negative 5 comma 0. All right, the x-coordinate and then the y-coordinate. So if we draw our coordinate system, I'll start by drawing the y-axis, and then I'll draw the x-axis, and then let's label them. This is the x, and this is the y. Our initial point is at negative 5 comma 0. So if we count our squares here, 1, 2, 3, 4, 5, this right here will be x equals negative 5. And so our initial point will be right there. All right, and so that's where our curve starts. And then the shape of our plane curve will be decided by our rectangular equation, right? We have y equals the square root of x plus 5. And we know that a square root function, at least a positive square root function, is shaped something like this. But in this case, we have the square root of x plus 5. So we need to shift that over 5 units to the left, which makes sense because our initial point is at the x value of negative 5. And so our plane curve will look like this. We start at this initial point and we move in this direction. All right, and so that's really all there is to sketching this plane curve. One other thing that we need to add is the direction of the curve, but it's pretty obvious in this case. We know we're starting at this initial point and we're heading in this direction, so just add a couple little arrows to indicate that that is the direction of that plane curve. It doesn't have an endpoint or a terminal point, and so we don't draw any points along that end. We leave it open because this is going to continue on forever. All right, and so that is it for this example. We have now completed our sketch of our plane curve that is represented by these two parametric equations, and we found the corresponding rectangular equation as well. All right, but before we end this example, I did want to show you an alternative way to graph a plane curve. If you get a rectangular equation from your parametric equations that you don't know how to graph, you don't know the shape of that rectangular equation, what you can always do instead is draw out a table of some t values of your choosing and the corresponding x values and y values that you would get by plugging in those values of t into the parametric equations. All right, so when t equals 0, if you plug that into each of these equations, you'll find that x equals negative 5 and y equals 0. When t equals 1, you'll get x equals negative 4, y equals 1, and so on. All right, and then what you can do is plot those coordinate points. You'll see I have them color-coded over here. And then once you have those points plotted on your coordinate system, you can connect them to draw your plane curve. And so you can see that we get the exact same shape as we got by graphing the rectangular equation for this plane curve. Okay, so however you like to do it is fine. Typically, I go with eliminating the parameter because I find it to be a quicker method, but you can always fall back to this method, which takes a little bit longer, but also works, of just drawing out a table of some t values and the corresponding x and y coordinates that you could plot to get the shape of your plane curve. Okay, and so with that, let's move on to our next example. All right, so next up, we want to sketch the curve represented by the parametric equations and find the corresponding rectangular equation by eliminating the parameter. All right, so this is the same exact type of problem as the last two examples, but now we have a new set of parametric equations. This time we have x is equal to 4 times cosine theta and y is equal to 3 times sine theta. And theta is greater than or equal to 0, but less than or equal to 2 pi. All right, so in this case, our parameter is not t, but rather theta. So sometimes your parameter can change. It doesn't always have to be t, and it doesn't always have to be theta either. It can be other letters as well. We just typically work with t and sometimes theta. But in this case, we know for a fact that theta is only defined for values from 0 to 2 pi, including both of those values. And that's going to be important later, so we'll come back to that. For now, what we want to work on is eliminating the parameter for these parametric equations. Now this is going to be a little bit different this time because now we're working with trig functions. We're not just working with algebraic expressions, and now we have trigonometric functions to deal with. And when you have trig functions in your parametric equations, and you're trying to eliminate the parameter, you don't want to try to solve for theta, or if you have t here instead, you don't want to try to solve for that parameter like we did in our other examples. Instead, you just want to solve for that trig function. All right, and so let me show you what I mean. If we divide both sides of this equation by 4, then we will isolate cosine of theta, and so we'll have cosine theta is equal to x divided by 4. All right, we divide both sides by 4, so we have x divided by 4. Now, if we do the same thing for this equation, but divide both sides by 3, we will have that sine theta is equal to y divided by 3. All right, and so this is what you want to get. You want to isolate your trig functions and have them equal to something in terms of x or y. At this point, you do not want to use an inverse trig function to solve for theta and then plug it into the other equation. That's not going to be very nice. It will be very messy and pretty inefficient. What you want to do instead is make use of your trigonometric identities. In this case, we're going to use the Pythagorean identity for sine and cosine. That's typically what you want to use when your parametric equations have cosine in one of them and sine in the other. All right, and that Pythagorean identity looks like this. Cosine squared theta plus sine squared theta is equal to 1. All right, so what we can do to convert these two parametric equations into a rectangular equation is use this Pythagorean identity. We can replace cosine squared theta with this expression, but squared, because if this is cosine theta, then cosine squared theta would be this fraction squared. And we can replace sine squared theta with this fraction squared. So if we do that, we will have x divided by 4 squared plus y divided by 3 squared. And that will be equal to 1. All right, now if we simplify, we will have x squared divided by 4 squared plus y squared divided by 3 squared is equal to 1. And at this point, you should be able to recognize this rectangular equation. This right here is an equation of an ellipse, or you can think of it as an oval, right? This is similar to the form of the equation of a circle, except we don't have the same denominator for x squared and y squared, right? We have 4 squared and 3 squared, and since those values are different, we're going to have an ellipse, not a circle. And specifically, this will be an ellipse that is centered at the origin because we have just x squared and just y squared. We don't have x and y added or subtracted to some other value and then have that whole quantity squared. We just have x squared and y squared, so this is going to be centered at the origin. All right, and so now that we have our rectangular equation, let's start drawing the sketch of this ellipse. All right, so I'm going to draw the y-axis, and then I'll draw the x-axis, and then I'll label them. So this is the x and this is the y. And let's draw our ellipse. Remember that the value squared beneath x squared tells you how far from the origin the ellipse is going to stretch in each x direction. So along the x-axis, our ellipse is going to reach +4 and -4. And then in the y direction, we have 3 squared underneath y squared. So 3 is going to be the distance from the origin or the center of the ellipse to the outside of the ellipse in the y direction. So it's going to stretch out to y equals 3 and y equals -3. Okay? And so our ellipse is going to cross through each of those points on those axes. And so this is what our ellipse will look like. It's not a perfect drawing, but it'll do. And so now we have the general shape of our plane curve. Now what we need to determine is our initial point, our terminal point, and the direction of this curve. All right, so we do know that our curve is going to be shaped like an oval or like an ellipse. We just need to know where does it start, where does it end, and where's it going. And so I'm just going to move our rectangular equation aside, and we will work on finding our initial and terminal points. All right, So our initial point is going to be when theta is equal to 0, the value of that lower bound. So let's start by finding the initial point. When theta equals 0, let's plug 0 into each of these parametric equations. First, let's start with the x equation. Cosine of 0 is equal to 1, so we'll have 1 times 4, and so x is equal to 4. Then for y, 0 plugged into sine is 0, so 0 times 3 is 0, and so y is equal to 0. All right, so our initial point is going to be at the coordinate point 4, 0. So if we start at the origin, 4, 0 would be right here. And so this is our initial point for this plane curve. Now let's find the terminal point when theta equals 2 pi, right? That is the upper bound of the values that theta can be. Theta can be from 0 to 2 pi. So if we plug in 2 pi into each of our parametric equations, we will get the coordinate point for that terminal point. And so when theta equals 2 pi, we'll plug 2 pi into the cosine function. Cosine of 2 pi is also equal to 1, so we'll have 1 times 4, which is equal to 4, so x will be equal to 4. And then 2 pi plugged into sine outputs 0, and 0 times 3 is 0. So we get the exact same point, right? The terminal point is the same as the initial point. We have 4, 0. So this point is the initial point, but it's also the terminal point. So we know that our curve starts at this point and makes a full circle, or I guess you would say a full ellipse, until it gets back to that point, but we don't know which direction it's moving. We don't know if it goes this way or if it goes this way. And so that's what we need to determine next. And the way I'm going to do that is just choose some value of theta between 0 and 2 pi to plug into our parametric equations and see what point it gives us. And we can plot that point, and that's going to tell us which way we're going. All right, and so I'm just going to choose pi. I'm going to let theta equal pi. Pi is in between 0 and 2 pi, so theta is allowed to be equal to pi. And so when theta is equal to pi, we'll plug pi into these parametric equations. Cosine of pi is equal to -1, so we have -1 times 4, which gives us that x is equal to -4. And then if we plug pi into this equation, sine of pi is equal to 0, and so 0 times 3 is 0. So now we're going to have y is equal to 0 again. And so let's plot this point. We have x equals -4 and y equals 0. So that will be the coordinate point -4, 0. And that will take us to this point right here, right? This is -4, 0. And this actually doesn't help us at all, unfortunately, because this is directly across from our initial point and our terminal point, right? We could take this path to get there and then get back to our terminal point, or we could take this path to get there and get back to our terminal point. So this point actually doesn't help us. We're going to have to find another point to figure out which way we're going here. And so let's try another value. This time let's use pi divided by 2. That's still within our interval for our parameter. And when theta equals pi divided by 2, we'll plug that into cosine. And cosine of pi divided by 2 is 0. So we have 0 times 4, which is 0. So x will be equal to 0. And then, if we put pi over 2 into this equation, sine of pi divided by 2 is 1, so we'll have 1 times 3, which is 3. So y is equal to 3. So now we have a good point here, right? We have the coordinate point 0, 3, which will take us to this point right here. And that point is going to help us determine the direction of this plane curve. We now know that we will be moving in this direction, right? Because if we're following the order of our values of theta, we start at theta equals 0, this initial point right here, and then the next value we would go to would be pi divided by 2, because that is smaller than pi and 2 pi, so this would be the next point that our path is going to travel to, right? Our curve is going to hit that point, then it will hit the point for theta equals pi, and then we'll make our way all the way back to theta equals 2 pi. And so we can add the little arrows to our curve to indicate the direction that it is headed. All right, you don't need to add as many as I did there. I just like to add a lot because I think it looks cool, but it doesn't matter. You can add 1 or 2. Just make sure that somebody looking at your graph can tell that this is the direction that the plane curve is headed. All right, and so with that, we found our rectangular equation for these parametric equations, and we sketched the plane curve represented by those parametric equations. Okay? And so with that, this is the last example where we're actually going to sketch a plane curve. Now what we're going to look at are some simpler examples where we just eliminate the parameter or just find some parametric equations for a given rectangular equation. All right, so here we want to eliminate the parameter and write the corresponding rectangular equation for the parametric equations. So here we have two parametric equations. We have x is equal to e to the power of negative t, and y is equal to e to the power of 2t minus 1. So what we want to do here is eliminate that parameter t by solving for t in one of the equations and then using that to plug into the other equation. All right, so I'm going to work with this one. This is a little bit more simpler. Let's see if we can solve for t. And what we can do in this case is take the natural log of both sides of the equation, because remember, the natural log and e are inverse functions, and so they're going to cancel out and allow us to isolate this exponent. So what we'll do is have the natural log of x is equal to the natural log of e to the power of negative t. Now, just like I said, the natural log and e will cancel out, so we're just going to have that the natural log of x is equal to negative t. And now to solve for t, we just have to multiply both sides by negative 1, and we'll have that t is equal to the negative natural log of x. All right, and so now that we have solved for t, we can substitute what it's equal to in for t in our other parametric equation that we didn't work with. So we will have y is equal to e to the power of 2 times t, which is the negative natural log of x, and then we're going to subtract 1. Now 2 times the negative natural log of x, that will be negative 2 times the natural log of x. So I'm just going to rewrite this. We will have negative 2 times the natural log of x as that exponent. And now remember that one of the properties of the natural log function, or just logarithms in general, is that if you have some constant times the natural log of some value, that is the same as having a natural log of that value to that power of a, right? A times the natural log of b is the same as the natural log of b to the power of a. That is one of the properties of logarithms that we can use. So in this case, we can take this negative 2 and make it the power of x. And once we do that, we can then simplify even further. So what we have here is that y is equal to e to the power of the natural log of x to the power of negative 2, right? We move that negative 2 out front to be the power of x, and we still have to subtract 1. And now e and the natural log will cancel each other out and leave us with x to the power of negative 2. All right, so we will have y is equal to x to the power of negative 2 minus 1, and we can move x to the power of negative 2 to the denominator of that term to make that exponent positive. And what we will have is that y is equal to 1 divided by x squared minus 1. And this right here is the rectangular equation that represents these parametric equations. We have now officially eliminated the parameter of t. All right, and now one more thing that I forgot to mention that you should probably add on to this answer is that since we took the natural log of x, the natural log function is only defined for positive values of x or values of x greater than 0. So because we took the natural log of x, this rectangular equation is only going to be defined when x is greater than 0. All right, we can't use any values of x that are less than or equal to 0 because the natural log of x is not defined for those values. All right, so that's just something to keep in mind. But this equation right here is the rectangular equation that corresponds to these parametric equations. Let's look at another example. All right, so next up we have this example. Once again, we want to eliminate the parameter and write the corresponding rectangular equation for the parametric equations. This time we have x equals sine of t and y equals cosine of 2 times t. Now in this case, in order to eliminate the parameter, we're going to need to make use of a double angle identity. In this case, we have cosine of 2t, that's the double angle. And so one of the double angle identities for cosine of 2t is that it will be equal to 1 minus 2 times sine squared of t. And I chose this one in particular because we have sine squared of t and x is equal to sine t. And so we can just replace sine squared t with x squared, right? If we square both sides of this equation, we'll have x squared is equal to sine squared t, right? So I'll write that out. X squared is equal to sine squared of t. And so we can replace sine squared t with x squared and have that y is equal to 1 minus 2 times x squared. And that right there is the rectangular equation that corresponds to these parametric equations. All right, so this is just a quick example of where knowing your double angle identities for your trig functions can be pretty helpful in eliminating the parameter for parametric equations. All right, so next up we have this example. Once again, we want to eliminate the parameter and write the corresponding rectangular equation for these parametric equations. We have x equals secant theta and y equals tangent squared theta. Now in this case, we can use another one of our trigonometric identities. In this case, we can use the Pythagorean identity for secant and tangent. And that identity looks like this. We know that 1 plus tangent squared theta is equal to secant squared theta. That's another one of our Pythagorean identities for our trig functions. And so we can replace tangent squared theta with y, because y is equal to tangent squared theta. So we'll have 1 plus y is equal to secant squared theta, but we know that secant theta is equal to x, and so secant squared theta will be equal to x squared, right? If we square both sides of this equation, x squared will be equal to secant squared theta. So we can replace secant squared theta with x squared, and now we have a rectangular equation that corresponds to these parametric equations. Now I always like to solve for y if I can, so I'm going to subtract 1 from both sides of the equation, and what we will have is that y is equal to x squared minus 1. And so that is our rectangular equation. All right, so next up we have a different example. This time we want to find a set of parametric equations for a circle centered at 3, 1 with a radius of 2. All right, so with the rest of our examples, we are going to be finding a set of parametric equations. So we're kind of doing the opposite of what we've been doing so far. We've been eliminating the parameter, but now we want to introduce a parameter and find a set of parametric equations. All right, so now in order to do this problem, we need to know the general form of the equation for a circle, right? We're going to start out with a rectangular equation, and then we're going to change it into being a set of parametric equations. All right, so remember that the general form of the equation for a circle is x minus h squared plus y minus k squared, and that's equal to the radius squared. Now, if your circle was centered at the origin, h and k would be equal to 0, because h and k just represent the x and y coordinate of the center of the circle. And so you're probably used to seeing x squared plus y squared is equal to r squared, but this is the more general form if your center is not the origin. So in this case, our circle is centered at 3, 1, and so 3 is the x coordinate of the center, so 3 will be h, and 1 is the y coordinate of the center, so k will be equal to 1. And then of course we're told that this circle has a radius of 2, so r is equal to 2. So what we'll have is x minus 3 squared plus y minus 1 squared is equal to 2 squared. All right, now if we want to represent this with parametric equations, just know that whenever you're working with a circle or even an ellipse, you're going to be using trig functions. So you're going to want to get this equation in the form of a Pythagorean identity. In this case, we want to work with sine and cosine. And so we're going to be looking to get this in a form of some value squared plus another value squared equal to 1. So all we have to do to meet that requirement is divide both sides by 2 squared, right? If we do that, we'll have x minus 3 squared divided by 2 squared plus y minus 1 squared divided by 2 squared is equal to 1. And now what we can do is set sine squared equal to one of these terms and cosine squared equal to the other term, right? Because we know that sine squared theta plus cosine squared theta is equal to 1. And so this matches up with this rectangular equation. We just have to set sine squared theta equal to this term and cosine squared theta equal to this term. Or we could swap the terms, it doesn't matter, as long as you use a different term for sine and cosine. All right, so we're going to let sine squared theta equal x minus 3 squared divided by 2 squared, and then cosine squared theta will be equal to y minus 1 squared divided by 2 squared. Now if we take the square root of both sides, then we will just have sine of theta and cosine of theta. And the reason we want to do that is because our end goal is to solve for x and y, right? Our parametric equations need to be a pair of equations where x and y are defined in terms of the parameter. So we need to get to x and y, and the first step to do that will be to take the square root of both sides of these equations. So we'll have sine theta is equal to x minus 3 divided by 2, and cosine theta is equal to y minus 1 divided by 2. And I don't think I mentioned it up until this point, but we're using theta as our parameter in this case instead of t. You could use t, you could have sine squared of t and cosine squared of t. I just like to use theta when working with trig functions. It doesn't really matter. It really just comes down to preference. All right, so now if I clean up my work, these are our two parametric equations so far, but we're not done yet. We still need to solve for x and y. So our next step is going to be to multiply both sides of these equations by 2. So what we'll have is 2 times sine theta is equal to x minus 3, and 2 times cosine theta is equal to y minus 1. And now what we can do is solve for x and y by adding 3 to both sides of this equation and adding 1 to both sides of this equation. So we will have that x is equal to 2 times sine theta plus 3, and y is equal to 2 times cosine theta plus 1. And those are the parametric equations that represent a circle centered at 3, 1 with a radius of 2. All right, let's look at a different example. So next up, we want to find a set of parametric equations for y equals x squared where t equals 4 at the point 4, 16. Okay, so in this case, we're given a rectangular equation and we're given a point at a specific value of t. Now, the way I like to handle these types of problems is first figure out what x would be based on that value of t. All right, because what we know is that when t equals 4, x is going to be equal to 4, right? When t equals 4, we have this point and the x-coordinate is 4. So when t is 4, x is 4. So what we can say here is that x is equal to t. That is going to be one of our parametric equations. And since we're saying that x is equal to t, well then we can replace x in this rectangular equation with t, and then we'd have y in terms of t, right? If x is equal to t, then x squared will be t squared. And so we'll have y is equal to t squared. And that will be our set of parametric equations. All right, and if we wanted to make sure that we still get this point when t equals 4, we have x equals 4, and y equals 4 squared, which is 16, which is what we have right here. All right, let's look at another example. Next up, we want to find a set of parametric equations for this rectangular equation, y is equal to 4x plus 1, where t equals -1 at the point -2, -7. All right, so in this case, when t equals -1, x equals -2, right? When t equals -1, our x-coordinate is -2. So what we can say here is that x is equal to 2 times t, right? If t is -1, if you multiply that by 2, you get -2. So we can say that x is equal to 2 times t. When t is -1, -1 times 2 gives us -2. And so since we're saying that x is equal to 2t, we can plug that in for x in this rectangular equation that we're given, and we can find the equation for y. All right, so we'll have y is equal to 4 times 2t plus 1, and that will give us y is equal to 8t plus 1. All right, 4 times 2t is 8t. And so y equals 8t plus 1 and x equals 2t are the parametric equations for this example. Okay, now these last two examples are probably the easiest out of all of the examples we've looked at so far. In this case, we have no restrictions. All we're told is to find a set of parametric equations for the rectangular equation. And so we just have y equals 8x minus 1, no requirements, just find a set of parametric equations. And this is a pretty easy process. The way I like to go about it is just let x equal t, and then rewrite y in terms of t. All right, so if we let x equal t, well, that's one parametric equation. And since x is equal to t, we can replace x with t and have that y is equal to 8t minus 1. And there we have a set of parametric equations for this rectangular equation. Now, this is not the only solution. There are multiple solutions. For example, we could also let t equal 8x. We don't have to just let t equal x. We can just pick that whole term, let t equal 8x. And if we solve for x, we'll have that x is equal to t divided by 8. If we divide both sides by 8. And then since we're saying t is equal to 8x, we can replace 8x with t in this equation to get our parametric equation for y. So we'll have y is equal to t minus 1. And so those would be another set of parametric equations for this rectangular equation. Let's look at one more example for this video. All right, so here's our last example. We want to find a set of parametric equations for the rectangular equation. In this case, we have y is equal to 4 divided by x minus 1. And just like with the last example, my go-to strategy is just to let x equal t. So we'll say that x is equal to t, and that's one parametric equation. And then because we're saying x is t, we can replace x with t and have that y is equal to 4 divided by t minus 1. That's definitely the easiest way to find a set of parametric equations, but another way that we could do it is to let t equal x minus 1. So if we did that, t is equal to x minus 1 then we need to solve for x. So we'll add 1 to both sides of the equation and have that x is equal to t plus 1. And then since we're saying x minus 1 is t, then that means that y will be equal to 4 divided by t. We just replace x minus 1 with t. And so there we have another set of parametric equations that would correspond to this rectangular equation. All right, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments below. But if you don't have any questions, this is all I had for now. So I will see you next time.